The reason why we begin our journey through the periodic table of elements with hydrogen and its atomic number or charge number is because hydrogen is the first and the lightest element due to its one proton. All other elements follow in atomic mass. Hydrogen has one proton, which is indicated by the number 1 here, the atomic mass. All other elements follow in atomic number. For example, helium has 2, lithium has 3, and so on. And that points us already at an important property of the periodic table of elements, in which the elements are arranged by their atomic number, their chemical properties, which are linked to the number of valence electrons along the columns, and these columns are called groups, and the number of electron shells along the rows, which are called periods. So the elements in the periodic table of elements are arranged by atomic number, by their chemical properties, which are linked to the valence electrons, and the valence electrons are indicated also by the number of the group. Indicated, it's not consistent, but the group number can already give us an indication of the number of valence electrons. We will look at that later. And we have the electron shells, so the chemical properties, and the electron shells. Along the groups, we have the chemical properties, and the electron shells are along the periods. The groups are the columns, and the periods are the rows. Just as a visual representation, the first shell, if we look at an atomic model, we have our atom nucleus, then we have the first shell, and the first shell can hold up to, at most, 2 electrons. One, 2. The second shell, if we redraw another atom, roughly like this. So the first shell can hold 2 electrons, and the second shell can hold up to 8. 1, 2, 3, 4, 5, 6, 7, 8 electrons. And the third shell can also hold up to 8 electrons. We have on the inner shell 2, then we have 8 electrons here, 3, 4, 5, 6, 7, 8, and on the third shell we have again 8 electrons, 2, 3, 4, 5, 6, 7, 8 electrons. Until the third shell is completely filled. So for example, all atoms along group 1 have one valence electron in their outer shell. And that would be the atomic model we already looked at, hydrogen, in our previous video. In that case, for hydrogen, we have only one valence electron. Valence means, and this is an important point, the power or capacity to react. We need to understand that it's the outer electrons that have the power to react with other atoms or molecules to form or break chemical bonds. So it is always these outer electrons which are involved in chemical reactions to form or break chemical bonds, not the electrons on the inner electron shells. So valence means, and this is important, valence means the power or capacity to react. And the reason why the outer electrons have this capacity is because of high and low energy states. So when we draw our graph here, like this, and we imagine we have two atoms that we bring closer together. Here they are pretty separate. Here they come a little bit closer together. And here we could imagine they have already bonded through the outer electrons. Then we could redraw the energy levels. Energy. And this would be, of course, our distance. then we could draw the graph somewhat like this. The closer we bring the two atoms together, the lower their energy state is. And the reasons why the valence electrons react with other elements is to reach a lower energy state that is preferred. And in the case of hydrogen, the electron shell already contains one electron, like we indicated here. And therefore, the shell is not completely filled and has a higher energy state, but the element would prefer to go to a lower energy state by filling the shell with a second electron and reach a noble gas configuration of helium through sharing electrons with another element. The noble gases, such as helium, neon, argon, have filled outer electron shells, and they are therefore unreactive. Helium has 2, neon has 8, argon has 8. And these electron configurations are particularly stable and have lower energy states because from observation we know these elements don't react with other elements, which is the reason why they're called noble. The noble gases have a lower energy state because their electron shells are filled. Their valence electrons in the outer electron shell is completely filled. And therefore they have a lower energy state. All other elements have this desire to reach the noble gas configuration, but they cannot do that alone, like the noble gases. They need a reaction partner to establish a chemical bond through shared electron pairs, which allows them to react and reach a lower energy state. So our hydrogen atom needs to find here a reaction partner with whom it can share one electron, so the two elements, of which one will be hydrogen, can form a covalent bond, and hydrogen can reach the noble gas configuration of helium with 2 outer electrons. At the same time, hydrogen provides already an electron, which gives another element the chance to reach noble gas configuration. Before we continue and look at an example, let's look at the new term covalent. Covalent consists of co and valent. Co comes from Latin and means together. And valent comes from valens, which comes from the Latin meaning of strength or power. which is the property the outer electrons have. They have the power to react. And so covalent could mean something like power together. And in a covalent bond, it's the valence electrons of an atom that can establish this bond through a shared electron pair, or through an electron transfer in an ionic bond. But we will speak about ionic bonds in another video. For the moment, let's take a closer look at an example for a covalent bond from the previous video, hydrochloric acid. Hydrogen is in group 1 and it has 1 valence electron. Chlorine is in group 17 and has 7 valence electrons. So hydrogen has 1 valence electron. Chlorine has 7. 1, 2, 3, 4, 5, 6, and 7. The reason why chlorine is in group 17 and not in group 7 is because of the transition metals here. They are counted before, so we have chlorine over here, but it has 7 valence electrons, and the transition metals here in this block, they are counted before this entire block here, and that is the reason why we come up to the group number 17 and not to the number 7. That is an oddity about the periodic table of elements, whereby the group number gives an indication of the valence electrons, but cannot be directly read from it in some cases. So when we bring hydrogen and chlorine closer together, we can notice something very interesting happening here. Hydrogen, and let's say our chlorine will be closer. Then we have 1 electron from our hydrogen. We have 1, 2, 3, 4, 5, 6, and 7 valence electrons from our chlorine, which means that now hydrogen has 2 valence electrons and chlorine has 8 valence electrons. Thereby, hydrogen reaches the noble gas configuration of helium with 2 outer electrons, and its valence electron shell is thereby completely filled, just like in the case of helium. And chlorine reaches its preferred noble gas configuration of argon with 8 outer electrons. And like that, we have a win-win situation and everybody's happy. Or on an even simpler covalent bond of hydrogen is hydrogen with hydrogen. So if we bring 2 hydrogen atoms close together, we have one electron from one hydrogen and another electron from the other hydrogen. Thereby, both hydrogens reach the noble gas configuration of helium with 2 outer electrons. both reach the noble gas configuration. Of helium. And this is something some gases do. They are called homonuclear diatomic gases. Homonuclear diatomic gases. Which is just a fancy way to say that they consist of the same atomic cores, and another good example of that would be oxygen. So oxygen, if we bring two oxygen close enough together, oxygen has 6 outer electrons, 1, 2, 3, 4, 5, 6, and the second oxygen atom has also 1, 2, 3, 4, 5, 6, and through that both oxygen have 1, 2, 3, 4, 5, 6, 7, 8, and here as well 1, 2, 3, 4, 5, 6, 7, 8, which corresponds for oxygen, which is in the second period, that corresponds to a noble gas configuration of neon. These homonuclear diatomic gases is something that some elements do, except of course the noble gases, which are monoatomic gases. The noble gases are monoatomic gases. And why would that be? Maybe you guessed it already. Their electron shells are completely filled and therefore they are unreactive. We also say that they have no affinity to react. The noble gases have no, we call it affinity. To react. The first shell in the periodic table of elements is indicated by this number, the period number, and the first shell, as we already said, can hold 2 until it is completely filled and reaches the noble gas configuration of helium. The second electron shell can hold up to 8 electrons, and the third outer electron shell can hold also up to 8 electrons, like we already indicated here. The periodic table of elements places a lot of importance on the number of protons and the number of electrons, as you may have already noticed. As you can see, the atomic number here the indication of the valence electrons and the number of electron shells have a prominent position, and the reason for this is very simple. It is the number of protons and outer electrons that determine the chemical properties of an element and how an element interacts with other elements to form or break chemical bonds between atoms or molecules in chemical reactions. When the elements are arranged in this way, there is a recurring pattern in their chemical properties called the periodic law. When the elements are arranged according to their chemical properties, we notice something that is defined in the periodic law, in which elements in the same column, which are called groups, have similar chemical properties because they have the same number of electrons in their last outer shell. For example, in group 1, we already saw hydrogen has one outer electron, just as well as lithium, sodium, potassium. And all elements have the tendency, for example, to react with oxygen relatively quickly to form their oxides. We have hydrogen oxide, which is H2O, or simply water. We have lithium oxide, which is written like this. We have sodium oxide, and so on. The periodicity of the elements in the periodic table is caused by the arrangement according to atomic mass and consequently of the periodic filling of the electron shells with electrons. And when elements have the same number of outer electrons, they tend to behave similarly in chemical interactions. There is a more complex explanation for the periodic behavior of the periodic table of elements, which involves orbital theory. But we will look at that in another video to keep it simple for the moment. For the moment, it is sufficient to understand that the periodicity of the periodic table of elements comes from the periodicity in the chemical properties. When elements are arranged by their atomic number, because the similarities in the chemical properties, by the way, were remarked more than a century before the idea of electron configurations, right? So people already knew that certain elements behave very similar, but they did not know that it is related to the number of protons and outer electrons. The history of the periodic table of elements is also rather remarkable. To conclude our section about hydrogen and the periodic table of elements, please allow me to read to you a small passage about the scientist who developed the visual representation of the elements we call today periodic table of elements. His name is Dmitry Mendeleev. The Russian chemist Dmitry Mendeleev was the first to observe that if elements were listed in order of atomic mass, they showed regular, periodical, repeating properties. He formulated his discovery in a periodic table of elements, now regarded as the backbone of modern chemistry. The crowning achievement of Mendeleev's periodic table lay in his prophecy of then undiscovered elements. In 1869, the year he published his periodic classification, the elements gallium, germanium and scandium were unknown. Mendeleev left spaces for them in his table and even predicted their atomic masses and other chemical properties. 6 years later, gallium was discovered, and his predictions were found to be accurate. Other discoveries followed, and their chemical behavior matched that predicted by Mendeleev. This remarkable man, the youngest in a family of 17 children, has left the scientific community with a classification system so powerful that it became the cornerstone in chemistry teaching and the predictions of new elements ever since. In 1955, element 101 was named after him, MD, Mendeleevium. So, pretty respectable guy, this Mendeleev. He was born in the 19th century and lived up into his 70s. And with this, we will close our video and look at the occurrence and the use of hydrogen in our next video.